Hello and welcome. I'm your host, Adam Hawkins. In each episode, I present a small batch of the theory and practices behind building a high-velocity software organization. Topics include DevOps, Lean, software architecture, continuous delivery, and conversations with industry leaders. Now, let's begin today's episode. Hello again. Adam here to continue the Saltside Chronicles. Previous episodes covered the run-up to the rewrite and the factors that created the Big Bang rewrite. This episode is a deep dive into the technical plan for paying back the technical debt and creating the next generation architecture. Allow me to begin by describing the system as it was and the specific challenges we faced. When the rewrite started, there were a handful of services without any real bounded contexts. There was a monolithic Rails app that served the desktop website and handled an extraordinary amount of back-office functions. There was a web service that served the mobile and feature phone versions of the website. This integrated with the monolith via a mix of APIs and shared libraries. There was also an admin service that managed the entire customer support end of the business. This included the business-critical features for reviewing, approving, and rejecting ads. The admin service communicated with the same DB as the monolith. As you can imagine, there were multiple problems with this architecture. The first is the config loading, which I discussed in depth in episode 2. Next is the horrendous and egregious boundary violation of sharing the same database across different services. That folds into the next issue, that there were no real APIs for core business functions like search ads or sign up user. Lastly is the gravity of the monolith. The monolith just did a lot of stuff. The more I learned, the more surprised I was. Even in hindsight, I'm surprised by just how much that codebase did. We discovered entirely unknown business support features that were split off into separate services over the course of the rewrite. This is not an exhaustive description of the system. All of the issues discussed in the previous episodes are layered on top and even stem from the underlying technical architecture. There were many ways to redesign this system from the ground up. My goal was to achieve these business and technical objectives. 1. A single API built, deployed, and operated by the platform team that supported customer-facing applications like the websites and mobile apps. 2. Separate the business logic and configuration. 3. Enable microservice architecture inside the platform team. 4. Speed up the time to launch a new market by making config editable by hand. 5. Use independent infrastructure for each market service environment. 6. Automate deployment of each market service environment through shared tooling. 7. Use shared tooling for every service built by the platform team and web team. And 8, and last but not least, avoid architecting the team into a corner. I was confident that we could achieve all these goals, especially since the team had already built the system once and we had a clear picture of the current technical issues. So I got to work sketching out and iterating on an architecture that could meet these objectives. The first piece of that puzzle was how to reorganize the current state of services into independently built, deployed, and operating services with data autonomy. Let's start with the design considerations for achieving that. A big factor in the final architecture was setting bounded contexts for each specific business domain, defining APIs, and avoiding cycles in the final service graph. Change rate was another factor. Certain areas of the system changed daily, some monthly, and some not even for years. I did not want to mix these concerns because tech debt matters more or less depending on the velocity. Another factor was ownership. I use the term loosely because the org structure at the time. The platform team managed all the APIs and infrastructure. The web team owned all the web experiences, including the internal-facing admin portal. The mobile team built the Android and iOS apps. I led the platform team. We were responsible for all the services that composed the quote backend. The scale of product requirements made it infeasible for one team member to operate at max capacity across all different parts of the product domain. An example of this is sending transactional emails to the user, maintaining config, payments, or handling ad reviews. I wanted bounded contexts that represented areas different members of the backend team could own in the sense that they'd be primarily working in those areas. These people would pair with others, review PRs, and make sure that changes met product requirements and were usable by downstream consumers. And most importantly, met our engineering standards. Then there is the data model itself. I'm still surprised to this day that such a complex system really only had two core data objects, add and user. Every one of these bounded contexts would operate on one or both of these in some way. So I did not think it was wise to allow each service to have its own representation of these two concepts. I know some domain-driven design people are shaking their finger at me, but oh well. Allowing each service to own its add representation could not work because of the relationship between add and config. This acted as a guardrail in creating services that mapped exclusively to entities. Instead, services focused on verbs instead of nouns. So how would all these services communicate? Bear in mind this is 2015. The company had used HTTP and JSON for years, and that was the status quo. I thought that using HTTP and JSON for all our internal service was a miscalculation at the time. Using HTTP and JSON would require that every service write API specs for requests and responses and then the underlying validation code. This opens the door to bike shedding over proper JSON design, which in turn leads to the creation of client code repeated in all consumer services. I wanted to avoid all that and instead focus on what mattered, easy communication across services. That led me to investigate RPC frameworks. We needed to support Ruby, Go, and Node.js. I investigated Protobuf but ultimately settled on Thrift. Choosing a binary format and generated code model effectively mitigated all those concerns and got the team focused on writing specs in the Thrift IDL. This was an amazing choice for multiple reasons. We could dry run the system design for topology flaws by writing all the Thrift files, then tracing flows across services and verifying there were no cycles. Plus, we could dry run the RPCs and structs themselves such that data required to complete the request was provided by the structs. Using Thrift also helped in defining differences in bounded contexts. We defined a common add and user struct and config structs in Thrift. Services exchanged these structs and then decorated them internally as needed. That kind of gives some aspect of the domain-driven design. But internally, this led us to use value objects by default as our architecture. Another factor was infrastructure isolation. We needed to move away from a single instance serving all markets to an instance per market. This meant moving from single infrastructure to n infrastructures, where n is the number of markets. Engineering was a bottleneck in this aspect of the business strategy. The business strategy called for moving into markets when the time was right. The previous market launch required months of just writing configuration in SQL. So I wanted to move engineering off the critical path here in a way that a new market could be quickly created whenever the business desired without impacting any of the other markets. This move to per-market infrastructure meant embracing automation and configuration such that market X could run at scale X and market Y at scale Y. This meant customizable vertical sizing of application instances in backing data stores like MongoDB or Elasticsearch, and customizable horizontal scaling for each market and each service. This serves as a nice segue between software architecture and infrastructure architecture. We decided that service was the unit of design in the system. I say service in the 12-factor app sense. A service was composed of 1 to n processes. Some processes could be web servers, they could be Thrift services, or background job processes, cron processes, or etc. The process itself made no difference. It was just a process. The only thing that did matter was load balancing. It was HTTP or TCP, vertical size, horizontal scaling, was it auto-scaled or fixed, ownership of data stores, language agnostic infrastructure, and independent development and deployment. I say independent development and deployment in the sense that a developer could clone the Git repo for one service, run the test suite, and then, if the test passed, deploy straight to production. The test suites covered all functional requirements and known regressions. Given any dependent service had a strict contract, defined in the Thrift IDL, then it's necessary and sufficient to say that if this service calls external service X and service X returns Y, then A, B, and C should happen. This behavior is testable completely through mocks and stubs. We had no reliance on an integrated environment like QA or staging. That was magical. Back to the infrastructure and software architecture. Docker had hit 1.0 throughout this time. We bet Docker would unlock 3 capabilities for our team. 1, language and runtime agnostic infrastructure and tooling by designing everything for containers. 2, removing language and runtime limitations from developers. Thrift supported the languages we used at the time, some we were interested in, and those we had zero interest in at the time, like Java, but that did come in handy years down the line. So if Go was the right choice for a service, then Go could be used. Just figure out how to build a Docker image and then you're good to deploy. And third, development environment standardization. It would be impractical to require every developer to maintain working environments for n different languages on their machine. Containerizing the development environment meant if a system had Make and Docker, then they were good to go. Docker did deliver on all 3 of these goals with the caveat on the first point around runtime agnostic infrastructure. Docker had just hit 1.0, so this was the very early days of the ecosystem. Best you could do was build a Docker image and push it to a registry. Getting that container running in production is up to you. There was no easily available community-supported and production-ready container orchestration tools. Kubernetes was still in development, and Mesos was probably the top contender at that time. Mesos, remember that? What about DCOS? How about that one? Today, we take Kubernetes' wide industry support and stability for granted. Now it's easy enough to just pay for Kubernetes. AWS has EKS, GCP has GKE, Azure has ACS, and even DigitalOcean has a hosted Kubernetes offering. None of this existed at the time. Our choice was to bind ourselves to a fledgling Mesos or DCOS open source project that might meet our requirements, or bite the bullet and build something Saltside specific from scratch. We had no intention of building an entire container orchestration system. We just needed a way to get Docker containers running behind a load balancer. Our previous deployment system was a simple blue-green strategy using golden images. So, moving to container orchestration would be a big jump in terms of complexity, let alone if the orchestration system worked. Ultimately, we decided to build our own solution to handle our per-market service and environment requirements. It was the less risky approach that didn't preclude us from adopting container orchestration systems in the future. Our solution was named Apollo. I say our solution, but the credit truly goes to my good friend Peter Aselius. Peter and I had brainstormed on what a solution would look like. It was largely inspired by Heroku. There was an apollo.json file that combined the proc file with config for vertical and horizontal scaling in each market and environment pair, as well as what data stores were required, like MongoDB, MySQL, Redis, etc. Again, this was not a container orchestration system. This was a solution for automating infrastructure that could run processes via a container. The solution generated a CloudFormation template that loaded EC2 instances with whatever was required to run the container. The instances ran in an autoscaling group that were connected to a load balancer. Rolling deploys happened with a script that used HAProxy to swap incoming connections between the running container and the next version. This provided zero downtime deploys. Infrastructure level changes, say to a backing data store or vertical or horizontal scaling, were deployed by a CloudFormation stack update. It worked out amazingly well. We used this tooling and infrastructure for a long time after the rewrite. But we did end up migrating to Kubernetes years later after the project had stabilized, but that's an entirely separate episode of the Saltside Chronicles. Docker plus Apollo provided us everything we needed from the infrastructure side. All we had to do now was just write the services. We ended up creating what you would call a hub and spoke design, although I think of it more like a solar system or a canalbula with a sun and orbiting bodies. Recall the state of the system before this whole thing started. There was a monolith that did all sorts of stuff, a web service and an admin service. Each service shared the same data stores and coordinated through client libraries for different things. There was no true ownership of different things with different concerns smeared across the system like cream cheese on a bagel, except it wasn't tasty. It was the opposite. hard to swallow, and completely unenjoyable. My mission was to untangle this mess by creating a service topology that relied on boundaries and did not have circular dependencies. Let me first address the God object at the root of many of these issues. That's the config. Recall that config is all the information about a market, such as the locations on a map, categories an ad may be posted in, and what data each ad requires. Given its importance, it's a global state that must be accessible at any part of the system. Previous systems stored config in a MySQL database. Code accessed this database via a client library whenever and wherever they needed it. This resulted in tens or even hundreds of database queries depending on the context. Also, config rarely changed. I think this turned out differently than originally designed. I gather it was assumed that config could be changed on demand through some sort of market admin dashboard. That never happened because of how intertwined the config and business logic was. Changing config required changing business logic, which meant code changes. The end result was that config was static in practice. It was dynamic in the sense that systems had to understand that different config flags could trigger different code paths, but not in the sense that config would vary in real time. Also, the quote whenever, wherever database query architecture was not suitable for a mobile app, so we needed something different. The fact that config was static enabled us to switch to a load once, use always model. Config became simple structs read at boot time, stored in memory, and then accessed that way. Zero latency, zero network overhead, and zero external dependencies. We created a DSL to write the config in a way that made sense to engineers and product owners. The same strategy applied to the backend services, web app, and mobile app. Load config once, and then update only when instructed to do so. Just a sidebar here, product owners actually reviewed PRs for config correctness since it was expressed in ways that engineers and product owners understood. It was also grokkable enough that a PO could make slight changes via the edit button on GitHub. That was 1000% better than the previous workflow. Anyway, this implied another change. Recall that there was a single instance for all markets. This required parameterizing every bit of code with the market since that informed which config to use. This created messy internals since there were many different ways to pass quote market around through the different layers. Some parts used HTTP headers. Some parts identified it from the ad in question. Others accepted it as a string as a function parameter. Ugh. The move to one instance per market implied that code would only serve one market for the lifetime of the process. As a result, there's no need for a market parameter with any external API or other function call. We also took significant steps to replace checks for if market equals X or category ID equals Y with feature flags in config. That made it easier to understand what the intended business purpose was. It also made it much easier to test. Surfacing a feature flag exposed the logic to all applications in the system so that they may be updated and act accordingly. I was ruthless in this area and encouraged all developers to be as well. Any PR that inferred behavior on market name or any other aspect of config was immediately rejected. This approach plagued the previous system and I would not repeat it. So at this point, we had moved away from the idea of dynamically loaded and real-time config. Instead, we used static config loaded once and stored in memory. Such an amazing change. Now the next question is, who owns the config? Config is the sun in my solar system analogy or the hub in the hub and spoke model. Config combined with add and user created the holy trinity of this system. They cannot be separated. So I put a bounded context around these three entities. This became the core service. The core service was the source of truth for all configuration, adds, and users. It contained three processes: a web server for the API used by the mobile and web applications, a thrift server for internal RPCs, and a background job processor. The design focused on creating the user-facing API and encapsulating common concerns across internal backend services. Non-essential logic was implemented in a command query architecture. The core service didn't index ads for searching. It told the search service to do that. The core service didn't handle reviewing ads. It told the review service to enqueue ads for review. The core service didn't send welcome emails. It told the email service to do that. In this way, the core service centralized as much of the business workflow as possible and delegated the implementation to other services. In some cases, other services reported back to the core service for their processing. This is where the hub and spoke model fits. Most traffic flows from the hub through the spokes to external services, and sometimes it flows back. Let me demonstrate using a key business workflow. It goes something like this. A user posts an ad. The ad is submitted to the review team. The customer support team reviews the ad and then decides to approve or reject it. If the ad is approved, then it's live on the site. If it's rejected, then the user is notified and requested to make changes. Once the user edits the ad, then the review cycle repeats. I must interject something at this point. This is an extremely terse summary. Saltside had hundreds of different business rules for this process. Ads could be auto-approved or rejected. A reviewer could reject an ad for a multitude of reasons. There were rules around automatically re-enqueuing ads. There were rules around delay time, spamming, and all sorts of stuff. In other words, this area of the system was extremely complicated. It was so complicated that no one person or even group of people, including engineering and product, fully understood the requirements. They only discovered them by comparing the new system to the old one. This was a powerful case for creating an architectural boundary between the core service, the review queue, and the internal admin app. So here's how we did it. Core service called the enqueueAdd RPC implemented by the review service. The review service managed the review queue. So it implemented all the business rules that could automatically approve an ad, reject it, or mark it as requiring manual review. It also tracked business KPIs like how long an ad waited in the queue. It provided a set of RPCs to access and manage the queue. The admin service represented the middleman between the review queue, the core service, and the customer support team handling all the back office work. It had two processes. One was the thrift server with RPCs for the review service, and the second was an HTTP and JSON API used by the admin app. The admin app was the internal tool used by the customer support team to review ads and a host of other critical business functions. Once the customer support team decided to approve or reject an ad, the admin service called the core service approve ad or reject ad RPC, and told the review service to remove the ad from the queue. This separated all the different concerns, primarily cleaving the user-facing and internal-facing flows into different code islands. It solved all of our problems and enabled new capabilities. In fact, it probably saved the rewrite a few times. 2 engineers were entirely responsible for this whole admin area, 1 platform engineer and 1 web engineer. The web engineer needed a running version of the admin service to develop their application. All backend services used hexagonal architecture, so the platform engineer built a development version of the admin API with a fake review service so it could be shared with the web engineer. All this was independent of any staging environments or any other parallel work. This established a fast and isolated feedback loop between the 2 of them and the product owners that enabled them to discover business requirements that no one knew existed at the start. This architecture paid dividends for years to come in other areas. The rules around approving and reviewing ads had some of the highest change rates across the system. Admin-focused product owners could quickly iterate on this process independent of everything else. So at this point, the design has the following services: core service, review service, and admin service. Core service managed config ads and users. Review service managed the review queue. Admin service coordinated things between the admin API, review service, and core service. This became the admin loop in the system because ads flowed from the core service through the review service via the enqueueAds RPCs, then through the admin service, and finally back to the core service via the approve and reject RPCs. So the admin loop got ads into the system. How do users find them? Well, that's where the search service comes in. What good is a classified site if users can't find what they're looking for? And of course, like most other things in this product, searching was far more complicated than it appeared on the surface. Why? Because config and other product requirements. Our solution was to declare a boundary and write the RPCs. We had many different search requirements. We decided to represent them with 2 different RPCs. One RPC handled searches done in the user-facing apps. The second RPC was a general purpose search intended for use by any internal service. You can kind of think of this as the lowest common denominator. This was a better solution than shifting unique search requirements into individual services because each service must index data. So whenever core service changed an ad, then it called search services index add RPC. This worked because core service was the only actor allowed to directly modify ads. The same solution applied to any other searchable entity. User searches hit the core API. The core API, that's the API used by the user-facing mobile and web applications, accepted calls in HTTP and JSON, transformed those to the relevant Thrift RPC call to the search service, then transformed the result back to HTTP and JSON. The admin service and review service were also heavy search consumers. The review service needed to make all kinds of searches for all the auto-approve and reject business rules. One such rule was automatically reject this ad if something is posted in the same category with a similar title and description in the past 3 days. The admin service used the general purpose search RPC to implement these rules and the massive searches inside the admin app and the customer support team needed with all kinds of filters. Regardless of the consumer, the core service told the search service to index stuff and then consumers could search for it through declared RPCs. This brings the service count up to core service, search service, review service, and admin service. These 4 services accounted for the bulk of the product. However, there were still more boundaries to create. I was lucky to work on a key feature before the rewrite started. It was my first serious contribution to the business. I wrote and launched the first paid feature in the product. Prior to that, everything had been free. But with the introduction of the paid features, users could purchase upgrades like promoted ad or bump ups. Promoted ads were featured in searches. Bump ups would continually move their ad to the top of the search results. These paid upgrades were designed to help users sell their stuff. Launching this feature included a web service for processing payments through various payment providers. This was a key requirement because we needed different payment providers for each market. This was especially complicated because it was hard enough to find payment providers for these developing markets. The payment service served up a list of payment gateways. A user could click on one and then be redirected through the payment flow on the gateway and then back through to our system. This boundary was already in place, so all we had to do was add the Thrift RPCs to integrate the existing payment service and the core service and the core API. So here's the services up to this point: core service, search service, review service, admin service, and payment service. So what happens after completing a payment? Well, the user needs an email receipt. Enter the email service. The email service represented a large chunk of business complexity. Again, it followed the established pattern of being more complicated than it appeared on the surface. The full requirements were not known at the beginning. Instead, they were discovered by comparing the old and new systems, then making whatever changes. Saltside email had an added quirk of dealing with translations, or localizations, depending on your preference. Also, the product had sent a lot of emails. Combine that with email-specific business logic and unique role to play in the business process made it easy to declare a boundary. The email service declared an RPC for every email sent by the product. Any service, likely the core service, could call the RPC to deliver the email. The caller would provide everything required, like the add-in user in the RPC, so email service had a functionally stateless design. We also built a live development environment using fixture data where developers could make code changes and then see HTML emails in their browser. It was great fun, plus it moved email implementation like customization and localization away from the caller. That kept everything cleanly separated and accessible to any actor in the system. This brings the services to the core service, search service, review service, admin service, payment service, and now email service. Now comes a group of services that fall into not changed often or no product owner or generally less important bucket. These were typically marketing related. Saltside didn't have a dedicated marketing person, let alone a team for it at this point. People had undertaken various initiatives that had made it to production, and unfortunately people had come and gone, leaving abandoned projects, but of course, a lot of it was still running in production. One such project generated a sitemap XML file. Luckily, one engineer had created a library for this functionality already. We extracted the existing bits into a new repo, and this became the sitemap service. I don't think it received any commits after we got it working. No changes in requirements equates to maintenance only in my mind, so let's keep that one over here with similar support levels. Another was Google remarketing. This is something to do with keyword generation and Google AdWords. I can't remember exactly what the point of this thing was, other than that there was certainly no person who could give clear requirements for it. All I can remember is that it loaded ads from the core service, then generated a CSV file of keywords and uploaded that to a place our Google AdWords account could read from. Then there was a third service for something I can't remember. That goes to show you how unimportant it was in the grand scheme of things. So here's the count so far. Core service, search service, review service, admin service, payment service, email service, sitemap service, remarketing service, and our unknown marketing service. There are still a few services that didn't make it into the summary, but that's the highlights. Each service was independently deployed and developed. It had full ownership of its data stores and API via declared thrift RPCs. All services shared a common definition of config entities, add, and user. All contextual information was passed into the RPC call to avoid cycle calls among services. All services were deployed to separate per-market infrastructure. This architecture solved the problems that plagued the previous system. I know that because I continued to work at Saltside for another 2.5 years after the rewrite. That allowed me to observe the long-tail impact of these architectural changes. I witnessed the architecture scale up to support twice as many developers. I witnessed those developers build and deploy and operate their own services. I witnessed the architectural boundaries hold and empower future product work. Saltside eventually did have their first profitable year. That would have never happened without the rewrite. I'm very happy with the role I played in this massive project and with the engineers I worked with. It was truly a technical success, but goddamn, it took way more time and effort than anyone expected. Now we're reaching the end of the Saltside Chronicles. All that's left is to revisit this undertaking through the lens of everything I know. Join me tomorrow for the final retrospective episode. That wraps up this batch. Visit smallbatches.fm for the show notes. Also find Small Batches FM on Twitter and leave your comments in the thread for this episode. More importantly, subscribe to this podcast for more episodes just like this one. If you enjoyed this episode, then tweet it or post it to your team's Slack or rate this show on iTunes. It all supports the show and helps me produce more Small Batches. Well, I hope to have you back again for the next episode. So until then, happy shipping. Are you feeling stuck trying to level up your skills deploying software? Then apply for my software delivery dojo. My dojo is a 4-week program designed to level up your skills building, deploying, and operating production systems. Each week, participants will go through theoretical and practical exercises led by me designed to hone the skills needed for continuous delivery. I'm offering this dojo at an amazingly affordable price to Small Batches listeners. Spots are limited, so apply now at softwaredeliverydojo.com. Like the sound of Small Batches? This episode was produced by Podsworth Media. That's podsworth.com.